Number 1, consider the polynomial p of x, whose graph is shown below. You do not need to factor this polynomial to answer these questions, so we don't actually have to worry about factoring that polynomial there. Part A, how many linear factors is p guaranteed to have? Explain. Well, we talked about the fundamental theorem of algebra today that says if I have an x to the 5th polynomial, this is a degree 5 polynomial. A degree 5 polynomial. A degree 5 polynomial implies that you should have 5 linear factors. I should be able to factor this into the product of 5 linear factors because it's a degree 5 polynomial. That's what the fundamental theorem of algebra says. Part B says, how many real zeros does P have? Well, the real zeros are where you hit the x-axis. It's where I hit the x-axis. Those are my real zeros. And it appears that there's 1, 2, 3. It appears that there's 3 real zeros. Why? Because I hit the x-axis 3 times. So, how many have to be complex? Well, if I have 5 linear factors, I have 3 zeros. It means I have to have 2 complex zeros. What do I know about these complex zeros? Well, we talked about that complex zeros come in conjugate pairs. So those two zeros must be conjugates of each other. If I have 1 plus I also have to have 1 minus I. They have to be conjugates because complex zeros come in conjugate pairs, which means that you're never going to have an odd number of complex zeros. You can never have 3 complex zeros because you would always have conjugate pairs. So you always have to have an even number of complex zeros. Number 2, consider p of x. Find all solutions to p of x equals 0. So I want to find when is this polynomial equal to 0? Well, this is a polynomial equation, and there's 3 things that need to take place. It needs to be set equal to 0. Check. It needs to be factored. Well, it's kind of factored. Let's tackle these quadratic terms. X squared plus 4. This is the sum of perfect squares. So this is x plus 2i, x minus 2i. X squared plus 1 is x minus I, x plus I. 2x plus 3, and 3x minus 4, because those are already linear terms. So, what are my zeros? Well, we use the zero product property now. What number do I have to plug in there to get 2i? Well, I get x equals negative 2i. X equals positive 2i. I minus I is 0, so x equals I. X equals negative I. Subtract the 3, divide by 2, x equals negative 3 halves. If I plug that in, I would get 0. And x equals 4 thirds, positive 4 thirds. That little dot should not be there, positive 4 thirds. So those are my zeros. I have 1, 2, 3, 4, 5, 6, which means this was a degree 6 polynomial. You may see your complex zeros written as x equals plus or minus 2i, and x equals plus or minus I, just to save some time, or space. But those are my 6 complex zeros because when I solve a polynomial equation, 3 things need to happen. It needs to be set equal to 0, needs to be factored, and then we need to use the zero product property, which says if I multiply 6 things together, one of these things has to be 0. Number 3, consider the polynomial p of x. Use the graph to find the real zeros of p. Well, the real zeros are where I hit the x-axis. Those are my x-intercepts. So it appears to be at x equals negative 1 and x equals 1, 2, 3. X equals 3. Those are my real zeros there. How many complex zeros must it have? Well, it's a degree 4 polynomial. I have 2 real zeros, which means I have to have 2 complex zeros. Because if it's a degree 4 polynomial, I should have 4 zeros between my real numbers and my complex numbers. Part C asks us to factor p by using the zeros from the graph. Well, I could try factoring this by grouping, but that's not going to work if you try that. So if I know my zeros, we can divide. If x equals negative 1 is a 0, what factor did that come from? I know one of the factors has to be x plus 1. You could also do this next process by using x equals the factor of x minus 3, but I'm going to use x plus 1. So I'm going to divide. I'm going to divide using long division for my long dividers out. Dividing what by x plus 1? x to the fourth minus 6x cubed plus 11x squared minus 18. Well, I need a 0 placeholder first, minus 18. Don't forget your placeholders. And we start the division process. So we say, what times x gives me x to the fourth? X cubed. Hopefully you remember long division. You guys are awesome long dividers. I'm not concerned about this. This one's a little lengthy, though. This division does take some time. And now I restart the process. Negative 7x squared times x is negative 7x cubed. Negative 7x squared. Change my signs to subtract, and I end up with 18x squared plus 0x, well, plus 18x, 18x squared plus 18x. Change my signs to subtract, and I get negative 18x minus 18. Well, that's times negative 18. And if you finish that 3, you get a remainder of 0, which is good. So I know that this polynomial here is a factor of our original polynomial. I could try to factor that by grouping, but unfortunately, that doesn't work either. So we're going to have to divide by our other 0. We're going to have to divide that by x minus 3. Because that's our other factor, x equals 3 is the 0, we're going to have to divide by the factor x minus 3. So I'll do reverse tabular for you reverse tabular people. I'm dividing this quotient here by our other 0. That way I can get all of the factors. Well, x squared times x is x cubed. X squared, that's negative 3x squared. But I want negative 7x squared, so I'm going to need another negative 4 of them. Negative 4x times negative 3 is 12x, but I want 18 of them, so plus 6. Not plus 6x, plus 6x. That is where the plus 6 is, negative 18. So it does factor. X minus 3 is a factor. Big idea here, this lets me write p of x. This lets me write my original polynomial as I have a factor of x plus 1, and I have a factor of x minus 3. I know that because those are my real zeros from the graph, and I also have a factor of x squared minus 4x plus 6. We should check if we can factor that quadratic, but I don't expect to be able to because it has complex solutions. What multiplies to 6 that adds to negative 4? There are no numbers that do that. There are no real numbers that do that. So that's an irreducible quadratic there. Let's not try to factor that right now. So now that I've factored it, part D wants us to find the zeros. Well, I already know 2 of the zeros. I know I have a 0 of x equals negative 1 and a 0 of x equals 3. We saw that from the graph. That's how we got those factors. I now need to know when is that other term equal to 0? Well, it's a quadratic that I need to solve, and I know I can't factor it, so you could complete the square if you remember how to use it. This would be a nice one to complete the square on, but we can use the quad formula. A equals 1, B is negative 4, and C is 6. Our discriminant, b squared minus 4ac, is negative 4 squared is 16, minus 4 times 1 times 6. So I get 16 minus 24. I have a discriminant of negative 8, which verifies my belief that I have complex zeros here because my discriminant's negative. My zeros are x equals negative b, so 4, plus or minus the square root of negative 8 over 2a. 2 times a is 2. Let's deal with that negative radical 8. I hate negatives under my radical because they're not real numbers, so let's take out that factor of I. I radical 8 is 2 radical 2 times I. So x equals 4 over 2 plus or minus 2 radical 2 over 2i, which gives me x equals 2 plus or minus radical 2i. Those are my other 2 zeros. So I know this polynomial has 4 zeros, x equals negative 1 and x equals 3. I found those right from the graph, which allowed me to divide in to find the other factors. Now that I have a quadratic factor, I was able to use the quadratic formula to solve that quadratic for when it was 0. That was 0, at these complex numbers, 2 plus radical 2i and 2 minus radical 2i. So hopefully you've enjoyed our study of polynomial functions, because we move on to trigonometry at this point. We move on from polynomials to go look at our trig functions, sine, cosine, and tangent, that we know and love from Common Core geometry. Hopefully you enjoyed this last problem. I had a lot of fun dividing twice. I'm assuming you did too.